So, today is Tuesday, December 1st. The first topic in our Unit 6 is area between curves. So this will be recording 6-1. Let's begin with 81AB2, free response. Now we're not doing the whole thing because part B is volume. We're not talking about that yet. We will in this unit. And on the back, the same thing. We're just doing like the first part of each question. Okay, so 81AB2 says, let's see, 81AB2 says, let R be the region of the first quadrant enclosed by the graphs of y equals 4 minus x squared and y equals 3x. Okay, so we want the area between these two curves in the first quadrant. Well, what are you going to do first? Let's graph it. Okay, now you can graph this by hand, but let's talk to Hal. Alrighty, here we go. And let's clear out some stuff. So, diamond y equals, let's put this in. So it's 4 minus x squared, just a parabola with a frown, right? With 0, 4 as the max y-intercept. You should be able to graph that without much trouble. And then what is the other one, 3x? All right, so 3x. And let's do, I don't know, a zoom 4. It's probably sufficient. And here's the parabola that goes through 0, 4. And it looks like it goes through 2, 0, negative 2, 0. And there's the line y equals 3x. mx plus b form, it's got to be a straight line, right? So what is the region? This is the region here, this. In the first quadrant, below the parabola and above the line. Now think Riemann rectangles. If you draw a Riemann rectangle between these two curves, what's the height of the rectangle? What's the height of the rectangle? Huh? It changes, right. But what is it in general? The upper y value minus the lower y value. In this case, the parabola minus the line. Okay? That's the main reason we want to graph this. Another reason is we want to know what the limits of integration are. Well, x equals 0, right? And x equals what? Is it 1? Yeah, 3 times x, it's in here, right? 3 times x, 3 times 1 is 3, and 4 minus 1 squared is 3. So clearly, if you don't see it, you can solve it algebraically or solve it right here. Do a F5 intersect. Just for fun, let's do it. F5 intersect. And there. And then the first curve is the parabola. There it is. So hit enter. The second curve is the line. There's only 2 curves. It doesn't matter which is which. And the lower bound is somewhere before, somewhere to the left of the intercept in x. So how about there? And somewhere after. And we get 1. Ta-da, but we knew that. Okay, so how do you set up this integral? The area that they want is the integral from 0 to 1 of what? 4 minus x squared quantity minus 3x, right? Okay. And that's the height of the rectangle. What's the width of the rectangle? The Riemann rectangle. What's missing? dx. Don't forget the dx. That's the width of each rectangle, right? Okay, so let's work this out. This isn't that terrible, is it? I guess you don't have to write this in standard form, and there's no combining like terms or anything, so just integrate. What do you get? The integral of 4 dx is usually what? 4x. The integral of negative x squared dx is negative x cubed over 3. And the integral of negative 3x will be negative 3x squared over 2. And we're going to plug in, according to the fundamental theorem of calculus, into this antiderivative, the 1 and the 0 and subtract. Let's make a little room. Now what's nice about 0? It just drops out. So we're really only evaluating at 1. So it's 4 minus a third minus a half. Now remember, this is 81AB2. They didn't have no calculators, okay? So what were we expected to do at this point, do you suppose? Get a common denominator. What is it? 6. So multiply top and bottom by 6 here, right? 24, 6. Multiply top and bottom by 2, so minus 2, 6. Multiply top and bottom by 3, so minus 3, 6. And what I do? Oh, I lost the 3. Whoops, sorry. Lost the 3. See, I don't have to take the AP. Okay, so when you plug in the 1, it's 3 halves. You multiply top and bottom by 3, it's 9, 6, right? All right, so minus 9, 6. So this is negative 11, and it's positive 24, so 13, 6. And you can always get a decimal equivalent if you feel like it, or a mixed number, and you're done. By the way, I can't see it, but what does this timer say? Can you see it? 5 minutes? Okay, I'm using a new recorder that takes longer to render. So I have to stop around 20. So when you see 20, scream. Literally. Okay, it's okay? All right. Because I can't see it from here. This projector sucks. All right, so that's 81AB2. Questions? That's all we're doing, just area today. All right, the next part was volume. I'm skipping that for now. All right, take a look at 83AB4 unless there's a question. 83AB4, let's do it. All right, 83AB4. The figure above shows a graph of the equation rad x plus rad y is 2. Okay. Let R be the shaded region. It's not shaded, but it's the region between the graph, the x-axis, and x equals 0 to x equals 1. Okay? Now, could you graph that on the calculator if you wanted to? How would you? You got to get y alone, right? So how do you get y alone? Add x, subtract rad x. Okay, so y equals 2 minus rad x. That's rad y, so what's y? 2 minus rad x squared, right? Okay, so that's really the function that we're dealing with. Let's see, let's graph that just for fun. See if it matches the graph they gave us. Go into y equals, I'm going to clear this out. I'll clear that out. And enter quantity 2 minus rad x. Where's the rad? There it is. Close the rad, close the quantity, squared, right? Enter it. And how about a zoom 4? And is that the graph they gave us? Come on, today would be nice. Where are you? Well, it's doing all these negative values that are undefined, so there you go. So that's the region we're talking about. And we're only talking about for x equals 0 to x equals 1. That's it. Okay, so how do you set that up, that area? I did all the work already, getting y alone, right? The idea is, let's see, let me make a little graph here. Oops. Let me do a little bit of a graphing thing. All right, so here's my y-axis, here's my x-axis. Alrighty. All right, and apparently it goes through the point 0,4 and the point 40, right? These are intercepts. If you plug in 40 or 0,4, it works, right? So it's not asymptotic to the axes. It's not really hyperbolic. I think it's called an astrid. If you keep this up, it's a star shape. If you keep this up in all 4 quadrants. All right, so we're talking from 0 to 1, right? This region here. But if you look at your Riemann rectangles, what's the height? What's the width? The height is the curve minus, well, it's this y and minus this y. What's the equation of the x-axis? Y equals 0, right? So technically it's still the big Y minus the little y, right? The big Y is this minus 0. Wow, okay. What's the width? Dx, okay? So the height is y and the width is dx, right? If you know the height of the Riemann rectangles and you know the width of the Riemann rectangles, you can set up the integral. Okay, so let's do that. Let's move this up a little bit. So it's going to be the integral from what? 0 to 1. Of what? Under what curve? Y minus x to the 1/2 squared, or rad x if you like. Okay. And how do you integrate that? Chain rule? Okay. So, chain rule isn't going to work, right? Why not? Because if u is the inner function, what's du? It's much more complicated than what I had. Right? If u is 2 minus x to the 1/2, then du is 1/2 x to the negative 1/2 dx. In other words, dx over 2 over rad x. There's nothing in here that matches that. I don't have any rad x down here. Okay? So this is not a u sub. So what's another way to go with this? Foil it out. Okay, good. So foil it out. Can you foil that in your head? 4 minus 4 rad x, right? Plus x. Okay, sounds good. Yep. We still didn't integrate. We're just setting it up so we can. So that's the height function in terms of x. That's the width in terms of x. Perfect. And these are limits of integration in terms of x. You need all the x stuff to match up. All right, anti-differentiate you get. 4 becomes 4x. Negative 4x to the 1/2 becomes x to the 3/2 divided by 3/2, which really means multiplied by 2/3, but I had a negative 4, so that's negative 8/3. Good. Plus x squared over 2. All right, and let's evaluate that from 0 to 1. Again, 0 is nice because it drops out. If it doesn't drop out, fine, plug it in. Plug in 1 is nice, that's easy. It's 4 minus 8/3 plus 1/2, right? Okay, again, common denominator, 6. So you get 24/6 minus what? 16/6 minus what? 3/6, right? Multiply top and bottom by 2, multiply top and bottom by 3. Oh, sorry, it's plus. And so we have, what is it? 24 minus 16 is? 8 plus 3 is 11/6. Wow, they like 6 for some reason. Okay, very good. So that's a typical area type question on the AP. All right, let's take a look at some more examples. Here's some more stuff. Kindly consider the following. Any questions on this one? We okay? Any problems with any of that stuff? All righty. What's it got here, 12? Am I saying that right? Okay. What if I want the area bounded by, let's see, what should I do? I'll make it green. Y equals rad x and y equals x minus 2 in quadrant 1. Just the area bounded by these curves in quadrant 1. Okay? Now, what the heck does that look like? Can you graph that without a HAL? Come on. You know what rad x looks like? You know what y equals mx plus b looks like, don't you? All right, let's just see how far we can get without a HAL. Quadrant 1. Okay, so here's my x-axis, here's my y-axis, my x-axis, and label stuff. Okay, so how do you graph y equals rad x? It's like a parabola that opens to the right, but it's a function, so it's only the top half, right? So something like this. Zing. Y equals rad x. And how do you graph y equals x minus 2? Well, the slope is 1, and the y-intercept is negative 2. Let's say negative 2 is down here. I probably should have made a little more room. And the slope of 1 is going to do something like this. Yeah, not quite. Wait, hang on. Let's put a negative 2 here. If that's negative 2, then that's positive 2. Let's make it a slope of 1. Something like that. Oh, I don't like it. Going. How about we do something like this? Oh, that. That's a little better. Let's say that. Okay? So we'll label that y equals x minus 2. Okay, so I want the area bounded by these two guys, but only in the first quadrant. So, ideas. There's a lot of ways you could do this. Let's see one setup. Ethan.
Well, because you're not, like, if you can't just do top minus bottom, then that's going to include the areas in the second quadrant, so you could do two integrals. One where you just do 0 to 2 of radical x, and then add on to it 2 to 4.
Okay, that's an idea. Let's do that. All right, so if we do the integral on the rad x from 0 to 2, obviously this is 2, yes? Because the slope is 1? Okay, let's see. So if we do the integral just on the rad x, that's rad x minus 0 technically, the x-axis. So it doesn't include this piece, does it? But then we need another integral for this area because the upper function and the lower function are different than the upper function and the lower function here, right? So set it up. What is the area then? It's going to be the integral from 0 to 1 under, the area under rad x, right? Or x to the 1/2, might as well do that because we're going to use the power rule probably. All right, so that's just this little section here, right? Yeah.
It should be from 0 to 2.
0, we said 2, right? Oops. Then we're going to add on the other area. Well, the other area is going to be from 2 to what? Well, I don't know. How do you know where they intersect? When does rad x equal x minus 2? That's what I want to know, what this x value is here, right? So I can go from 2 to whatever. This is not necessarily drawn to scale, by the way. It's 4, you can eyeball it, right? Can't you say rad 4 is 2 and 4 minus 2 is 2, right? If you want, you can solve this algebraically, square both sides, or you can solve it on the calculator, intersect, y1, y2, whatever. It's 4. So the limits of integration in terms of x are 2 to 4. Okay. Under what now? What's the height function here? See, the height function here for the Riemann rectangle is different than the height function here, right? So what's the height function? Minus that. Okay, so let's write that. Rad x, I'm going to write this right. X to the 1/2 minus quantity x minus 2. Be careful how you subtract, you add the opposite. So I need all parentheses here. And that's the height function. What's the width? dx. Don't forget the dx, very important. Okay, so we should be able to work this out, no problem. What's the antiderivative of x to the 1/2? X to the 3/2 times 2/3. Good. Evaluated from 0 to 2. Okay, plus, well, the same thing here, yes? Now, technically, I guess maybe I should distribute the negative. Isn't this x to the 1/2 minus x plus 2, really? Okay, so let's integrate that. So it's going to be the x to the 3/2 times 2/3 again, minus x squared over 2 plus 2x. Good. All of that is being evaluated from 2 to 4. Okay. So plug in 2 and you get 2/3 times 2 to the 3/2. Plug in 0, drops out, right? Okay, plus, now let's see, plug in 4, you get 2/3 times 4 to the 3/2 minus 4 squared over 2 plus 2 times 4. That minus, what happens at 2? Yeah, running out of room. Okay, how about if I put it down here? Minus, now let's plug in 2. 2/3 of 2 to the 3/2 minus 2 squared over 2 plus 2 times 2. Okay, so what does that work out to be? Well, well, this isn't that bad. What's 4 to the 1/2? 2 cubed. 8 times 2, 16. Okay, so I got 16/3 here. This is weird, but what do you notice here? So what's going to happen? They're going to cancel, so I don't really care about this term, right? So that's why I'm starting here. So this was, what did we say now? It's 2, 8, 16/3. Okay, that's 16/3. What's this thing? 8, right? 4 squared is 16, over 2 is 8, so minus 8. And this is plus 8. All right, so this whole parentheses here is just 16/3. This drops out, this drops out. Now we're going to subtract a negative, which really means add, right? But adding what? What is this? 2. So I'm going to add 2, but I'm going to subtract what? 4. So I'm really subtracting 2. So this is 16/3 minus 2, and if you like, that's 2 over 1, so 16/3 minus what? 6/3 is 10/3. Okay? Alrighty. Fine. But wait, there was an easier way. Was there not? Look at this. Look at all the work you did to integrate this piece, right?
20.
I'll get to that. But staying in vertical strips for the moment.
20 minutes.
What? 20 minutes? Oh, God, no. Okay. Wait, okay, 20 minutes. Hang on, I just got to save this. Bing.